Alright, ladies and gentlemen. So, as we get started with lesson number 7, we are transforming exponential functions. So I've included our learning goals, success criteria, and practice questions from the hub page. This is mostly because typing out on Explain Everything is pretty difficult. So I'll give you all a minute to read over the learning goals and success criteria. Please note that in this section of the course, your textbook actually changes the way in which we name our transformations. Instead of A, B, C, and D, we're now going to be using A, K, D, and C. Alright, and we have our transformation form given to us right here so that we can review the way these transformations are applied. Alright, when we get into transforming exponential functions, we have b raised to the exponent x as the parent function, where b is a base, not a variable. Okay, so what I mean by that is if we're looking at 2 raised to the exponent x, we're looking at 1 over 4 to the exponent x, then our base would be 1 over 4. The way we apply our transformations is the same as we've done previously to different parent functions. We have a being our initial value, as well as what determines our vertical stretches, compressions, and reflections. C is going to determine vertical shifts up or down. K will determine horizontal stretches, compressions, and reflections. And D will determine horizontal shifts left or right. The one new piece of information here is this use of the initial value. Okay? That initial value is talking about what we get when x equals 0. So if you have a times b to the exponent x, b to the exponent 0 will give you 1. 1 times a will give you the value of a. So the y-intercept will be determined based off of interactions of this initial value and our c value, which will shift up or down. Okay, so it's not as simple as what we saw previously with other functions. We need to consider the fact that you're going to have a base raised to the exponent 0. You're then going to multiply that by a to get an initial value, and you're going to shift that up or down. Okay, more to come on that as we get further into it. Alright, so we're going to start off by reviewing a few concepts, and then we're going to look at some transformations. To begin, we're going to look at our parent function and the way we transform these functions. So as I had mentioned previously, this b here is not a variable, and it's not something that we would consider to be a coefficient. This is talking about our base. And our base determines our growth or decay. We looked at growth or decay in lesson 6. So if the value is greater than 1, we're going to see exponential growth. And if the value is between 0 and 1, we're going to see exponential decay. Our variable x changes as we move to the left or to the right, and this is where we see those curves which will grow or decay, right? So if we have our Cartesian plane here, we could have a growth curve that's going to forever increase to the right and forever approach 0 to the left. If we're dealing with exponential decay, it's the opposite. They're going to have the same y-intercept if they have the same reciprocal bases, but we're going to forever increase to the left and we're going to forever decrease to the right if we're dealing with exponential decay. Our transformations are the same as we saw before. So we have a as a coefficient. We have c shifting us up or down after the fact. And we have all of those transformations on x happening. H will be multiplied in. So remember that you always have to present it in factored form. You can't have h times x minus d. You have to have h times all of x minus d within brackets. Okay? Just things to keep yourselves aware of. Notice, all the transformations on x happen in the exponent. Another topic to look at quickly is our mapping notation. We can all recall that our mapping notation takes our points x, y, and it transforms them using our transformations on x and on y. So we're going to apply our horizontal stretches or compressions using the value of h. We're going to shift left or right based on the value of d. We are going to stretch or compress vertically by a. We'll also reflect if a is negative. And we're going to shift up or down based on the value of c. Last of all, I want to talk about our key points because determining key points requires us to consider our base. So we know that our key points are always going to be the x and y values of our parent function, right? And we can just construct a table of values that goes from, say, -2 to +2, just for time's sake. But your key point's value of y is always dictated based on b. So let's say we have f at x being equal to 2 raised to the exponent x. If that's the case, then you're going to see 2 raised to the exponent of -2, 2 raised to the exponent of -1, 2 raised to the exponent of 0, 2 raised to the exponent of 1, and 2 raised to the exponent of 2. Okay, so we'll apply our rules for negative exponents. That's going to put us 1 over 2 to the power of 2, which is 1 over 4. Next we'll see 1 over 2 to the power of 1, which is 1 over 2. The rule for a 0 exponent is that 2 to the power of 0 is 1. 2 to the power of 1 is 2, and 2 to the power of 2 is 4. This would not be the same series of key points if we change our base. So if we were to then use 3 as our base, we would see a different outcome, as we'll see on our next page. So if we were to use f at x is equal to 3 to the power of x, when we looked at our key points, we're going to use the same inputs, and we would end up with 3 to the power of -2, which is going to give us 1 over 3 times 3, or 1 over 9. We'd then get 3 to the power of -1, so 1 over 3. We would have 3 to the power of 0, which is 1. 3 to the power of 1, which is 3. And 3 to the power of 2, which is 9. Okay? I'm not going to do any more examples of key points. Just remember that whenever you're working with these functions, you have to develop your key points based on your base. You should be doing this anytime you transform these functions because as we change our bases for exponential growth and exponential decay, we're going to need to use those key points to then transform. So now we're going to start looking at the actual transformations applied to our function. For the examples that we're looking at right here, we're going to start off with f at x being equal to a base of 2 to the exponent x. Okay, and that's going to be the red line in all of our slides. I'm going to be applying specific transformations to each of them, and fortunately we're zoomed in enough where you can actually see the grid and see how the points will change. I'm going to be putting in one transformation at a time. So we're going to start by looking at the impact of A, and we're going to see what happens when we vertically stretch, when we vertically compress, and when we vertically reflect. So to begin, we have f at x equals 2x, and here we add that we are going to use a transformation on A that will vertically stretch. So what we see here is our red line that represents f at x, and this new blue line is going to be a transformation that we will call g at x. And in this case, we've got an a value of 3 multiplied into 2 to the power of x. Okay? Few things to notice here. We see each of our points vertically stretched up. Okay, so for example, our y-intercept of 1 is now a y-intercept of 3. The reason for that being, if we sub in x as 0, we will get 3 times 2 to the exponent 0, which is 3 times 1, or 3. Okay, and that happens everywhere. We see at negative 2, we were originally dealing with 1 over 2 to the power of negative 2, giving us this point here of negative 2 and 0.25. Well, we then multiply that by our value of a, stretching it up to a new y value of 0.75. And that's going to happen for every point. Okay, so that's our vertical stretch, something that we are very familiar with. We're all used to seeing those points being pulled upward by a factor of a. In this case, we see a vertical stretch by a factor of 3. This means that the y value in each key point has been multiplied by 3. We're now going to add a green function, and this is going to introduce a vertical compression. So we've looked at f at x and g at x. Let's look at h at x being equal to an a value of 1/2 multiplied by 2 to the power of x. Okay, and when we get into questions like this, I'm noticing some people making some algebra errors by saying things like the 1 over 2 times 2 will cancel. That's not true. And the reason it's not true is we have our exponent only applied to 2. Right? We've got 2 to the power of x, and the answer to that gets multiplied by 1/2. Okay, so there's no canceling here. There is a vertical compression to our y value. We see that our points have all been vertically compressed down by a factor of 2, meaning we've divided the value of each of these y values by 2. Right? 1 was divided by 2 to give us 0.5 right here. Y value of 4 was divided by 2 to give us a new location at y equals 2, and that's present across the entire function. Okay? I know that this is a bit slow, but I wanted to provide a detailed review of how the vertical stretch and vertical compression happens and how we would discuss it. So here we're looking at a vertical compression by a factor of 2. Last of all, we introduce our purple line here. I don't have a purple color in Explain Everything, but what we're looking at is y is equal to negative 1 multiplied by 2 to the x. And I'm writing it this way so that we can identify our a value as being negative 1. Okay, and that's caused our vertical reflection. And as we can see on our actual graph, we started out with a y-intercept at 1. Well, our new y-intercept is down here at negative 1. When x equals 2, y was equal to 4. Now when x is 2, y is equal to negative 4. So we just see that the y value is being multiplied by negative 1 in each case. Alright, so that sums up the different impacts that the value of a can have in terms of transforming the points. Okay, one thing that I want to caution everyone against is by looking at this graph, people often assume that the value of a is the y-intercept. That is not correct. Okay, the value of a is part of how we determine our y-intercept, but we need to also consider how c impacts things, and we're going to look at that next. Alright, so now that we've looked at a, we're going to take a look at the impact of c. Once again, our red line is f at x is equal to 2 raised to the power of x. We can see our y-intercept here is at 1, and we can see that when x is equal to 1, y is equal to 2. These are two important characteristics. We can use that to take a look at what our base actually is going to be equal to, but we need to also recognize that we've got our horizontal asymptote here happening at y is equal to 0. Okay, an important characteristic that is often overlooked. So when we're looking at these functions, we need to recognize that this line will forever approach 0 as we move to the left, but it will never actually reach it. Okay, this is going to come in again shortly as we start to look at these transformations. So we're going to introduce our first transformation here. We can see our new g at x is going to be 2 raised to the power of x plus, in this case, 4. We know that it's plus 4 because we can see our horizontal asymptote is at 4. Okay, so there's our vertical shift. You're not going to be looking at things like the y-intercept to determine your shift, right? I know that right now you can see this and say, well, you've just added 4 to 1 in order to arrive at 5, but remember, the y-intercept is determined by interactions between both A and C. So we're not going to use that as our method for determining. We want to be looking at where the actual horizontal asymptote comes into play. We add another function here. In this case, we're looking at h at x is equal to 2 raised to the power of x minus 2. And again, we got that minus 2 by our horizontal asymptote being present at -2. Okay, so just as we've seen before, C is going to shift all of our points up or down by the value of C. We need to recognize that we get our C value not from the y-intercept, but rather from where our horizontal asymptote is located. We're now going to look at an example that has a vertical stretch as well as a vertical shift. So here we see f at x, which is our red line, and our transformed function here, which is our black line. We can see that we've shifted up by 1 because our horizontal asymptote is running at y equals 1. Therefore, C must be equal to 1. But we can also see that our y-intercept here is not following the pattern that we would see from f at x, mainly a horizontal asymptote at 0 and a y-intercept at 1. Instead, we see that we have a horizontal asymptote at 1 and a y-intercept all the way up at 4. This has happened because not only have we shifted up, we have also done a horizontal stretch. Okay, so 4 is equal to the value of C plus the value of A. We know that C equals 1, so this is 4 equals 1 plus A, therefore A is equal to 3. So what we have here is our function, which we'll call g at x for this example, being created by a vertical stretch by a factor of 3 applied to our base of 2 raised to the exponent x, and then we shift up by 1. Alright, so the reason I'm going through this is you need to be able to read these graphs and understand the transformations, as well as be able to transform them using an equation and key points. Alright? This is an area that can cause people to get tripped up, and the most important thing to do is just remember that you've got to slow it down. When you're looking at these functions, first find your horizontal asymptote, then look at your y-intercept, and together use those things to determine the values of A and C. Alright, so now we're going to get into some of the horizontal transformations. We start off again with f at x being equal to 2 to the power of x. And here we introduce our new g at x, our blue function, that is showing a horizontal compression. So what we see are our points are being drawn in towards the y-axis. Alright, and we can see here that it wasn't a nice division that happened. What we see happening here instead is that we've divided the values by 3. So we have an original value of x equals 2 being divided by 3 to give us our new location, and when x equals -2 down here and we divide it by 3, we end up with our new location as well. Okay, so how we see this is that g at x is being transformed not on our base, but up in our exponent. We're going to see 3 being used as a coefficient on x. All right, and remember that those horizontal stretches and compressions are presented opposite to the way they're applied. So we see this as 3 times x, but it's actually applied by dividing by 3. Okay, and the reason for this, if you recall, is that we can fit this distance from the y-axis to our transformed location, we can fit that in 3 times to reach our location on the parent function. Okay, so there are 3 exponential growth curves for g at x in order to occupy the same horizontal space occupied by our parent function. We put in another function here that's demonstrating our points being stretched outwards. So our horizontal expansion, or our horizontal stretch, is being accomplished here in h at x, where we see that h at x is equal to 2 raised to the power of 1/2 times x. And again, this means that we are going to multiply the value of x by 2, but the way that it's presented is opposite. Recall that we interpret this by saying if we were at the location for x, that would only be half the distance covered by our transformation as opposed to the parent function. Okay, and I know that this sometimes gives people difficulty. It's really a matter of understanding how much of your parent function will be present when you transform it. So if you are stretching by a factor of 2, you will get half as much of the function in the same space as you would get with the parent function. If you're compressing it, then you will get that many times the transformed function within the same space as the parent function. I haven't bothered to put a slide up of horizontal reflections, okay, but it's the exact same idea. We would just see a relocation of the points from f at x from being in the positive domain moved over to the negative domain. So if we were to quickly sketch it out here, we would see our curve look like, oh, I went a little bit below the axis there. Pay that no regard, but that's the idea there. That would be what happens when we put a negative in the exponent. So if we were to talk about j at x, we would be looking at 2 raised to the negative x. Okay? Another way of interpreting that is that we have 1 over 2 raised to the power of x by applying our rule for negative exponents. And this is why when we horizontally reflect, we go from having a growth curve to a decay curve. Or if we started with a decay curve, we would reflect and get a growth curve. We're going to take a look at the last transformation, which is our horizontal shifts left and right. I'm just going to put up a single slide demonstrating the 3, and that will wrap up the applications of these transformations. Alright, and here we are with our 3 functions, our red line again being f at x, we'll call our blue line g at x, and we're witnessing some horizontal shifts left and right. So what I tend to do with these is look at where your y-intercept has been relocated to horizontally. So we have moved 3 to the right. So that means that our function, which was 2 to the power of x, has moved 3 to the right, so we are subtracting 3. Okay, there's our horizontal transformation, 3 units to the right. Now if we're looking here, we'll do the same idea. We're moving back 2, so that would mean that h at x has seen our base of 2 to the power of x being moved 2 to the left. So we add 2. Alright, so there's each of these transformations applied individually. Now obviously we're moving towards applying these transformations all together. So for today's activity, we're going to be focusing on describing the transformations and presenting the proper mapping notation. So having worked through each of these transformations, you should now be moving on and looking first of all at the investigation in chapter 4.6, Transformations of Exponential Functions. So you're going to be going through and you're going to apply transformations using each of the ideas we've covered. So you're going to be vertically stretching and compressing, you're going to be horizontally stretching and compressing, vertically shifting up and down, and horizontally shifting up and down by applying A, K, C, and D. When you get to the practice questions, you're going to be given equations and asked to list the transformations. Okay? You are going to be given transformed functions, and they're going to talk about the order in which things should be applied. What they're really just talking about is how you would create your mapping notation, okay? Remembering that order of operations must be followed, so that means that we're more concerned with our vertical stretches, compressions, and reflections, and our horizontal stretches, compressions, and reflections than we are with our shifts, because we need to reflect, stretch, or compress before we can move left or right or up and down. Okay, that's all that they're trying to get at in that section. You're also going to be given graphs, and you're going to have to determine what transformations have been applied, either by matching or by interpreting what's actually happened. For these questions, I think it's a good idea, if you're having trouble, to map it out in Desmos and see what's happening. Another strategy that you can use is identify what your base is. So, for example, one of the questions in the textbook says that f at x is equal to negative 1 over 4 to the negative x plus 3. Well, we can see here that our base is going to be negative 1 over 4. So you can get your key points. So x and y equals 1 over 4 to the power of x. Alright, and then go from negative 2 to positive 2, get your key points, build your mapping notation, and then determine what your new points are going to be by applying x over h plus d and ay plus c. So by filling this table out, you'll know where your points should be, and you can then match it to the graph. Okay? Either of those strategies are good. I would recommend that you work on this strategy because you're not going to have access to Desmos when you take advanced functions next year and have to do these types of questions in a test. Okay? Another reason that I recommend this is it's unrealistic to expect to just look at a graph and know what all the transformations are. Like, over time, you will develop a greater understanding of these transformations, but I don't think that at this stage you're at that level. Okay? So just take a bit of time and make sure that you're working through these thoroughly. I realize that this is a rather involved lesson, and it does require a fair bit of work. Now, I want to make sure that everyone is maintaining that 3 hours of work a week. Okay? You shouldn't be having to spend like 5-6 hours. So I've made sure that our next lesson, applications, doesn't happen until May 7th. That gives you a fair bit of time to work through this week, and also to email me with any questions, okay? So if you're having trouble, let me know, and we can work out a way in which your workload can be reduced for the remainder of the week. All right? That's everything from me. Make sure you try out the investigation at the start of 4.6 and then get going on those practice questions, okay? Good luck. Hope everyone is doing well, and bye for now.